Okay, number 5. The time of fall is going to be, well, if I release a pendulum next to the wall and it swings and hits the wall, then it's undergone 1/4 of a cycle. Because the full cycle would be from here to equilibrium, which is where the wall is, and then past equilibrium, and then back to equilibrium and back to the original point. That would be 4 times the just released to wall time. Okay, so the time of fall would be 1.7 seconds over 4.425 seconds. If the distance of fall is 1 meter, then it's easy to calculate the acceleration. You can use formulas, but let's just do the straightforward reasoning, which is just as easy as the formulas. Average velocity is 1 meter over 0.425 seconds, and that's going to be approximately 2.3 meters per second. Of course, I'm not watching significant figures at all here. That 0.425 is probably way too many significant figures for the accuracy of the swing of the pendulum, especially for the number of significant figures given here. Still, we'll use it, but we'll say the average velocity is about 2.3 meters per second. The object is said to have started from rest. It's been dropped at the same instant the pendulum was released, so the final velocity would be twice the average velocity, since initial velocity was 0. And from that, we're going to get a 4.6 meter per second final velocity, which we're going to divide by the time interval to get the rate at which the velocity changes, which is the acceleration. In my estimate here for this calculation, based on this 2.3 meter per second, is 10.8 meters per second squared. I have a feeling that might be closer to 2.2 meters per second, although I don't really see that. But if you do the calculation correctly and then take account of the fact that you have a 3% or a 0.03 second uncertainty in that 1.7 seconds. So you might figure this based on the 1.67 and the 1.73 seconds and see if this falls into the range of the known acceleration of gravity, or the generally accepted value, which is very close to 9.8 meters per second squared. Okay, so let's just think that 1.7 seconds plus or minus 0.03 seconds, that plus or minus 0.03 seconds is about 2% of 1.7 seconds. So we have an uncertainty of about plus or minus 2% in our time of fall. When we divide our distance by our time of fall, then our result is going to be uncertain by about plus or minus 2%. And we use that result to get our final velocity, therefore our change in velocity. So that's already uncertain by plus or minus 2%. And we divide by delta t, which is again still uncertain by plus or minus 2%. So we get now a plus or minus 4% uncertainty. So with a plus or minus 4% uncertainty and an approximately 10 meter per second squared result, we get plus or minus about 0.4 meters per second squared. Now that still doesn't bring this within the range of the accepted value, and I think even if you use the accurate results, it doesn't come out within that range if that's your uncertainty. The 1.7 seconds plus or minus 0.03 seconds is probably an overestimate of the accuracy you can get with this kind of experiment. Okay, 0.03 seconds is roughly the uncertainty you would expect due to the inability of your ear to distinguish two sounds that are any closer together than that. But there are other, you could measure the cycle of the pendulum incorrectly, although that could be done with a lot of precision. So there are various things that might influence this experiment, which we will do, and want to try to understand as much as we can.